So at this point, we've worked on some topics where we have motion in a horizontal direction. Like, for example, if you take a ball and roll it along the floor. We've also looked at motion in a vertical direction. So if you, for example, take a ball and throw it straight up and have it come straight back down along the same path. What we want to get to is a point where we can have an object that's moving in both the horizontal and vertical direction at the same time. So to demonstrate that, maybe imagine you are throwing a ball in the air, but rather than throwing it straight up, you throw it kind of at an angle, sort of up, but sort of to the side. Now, what's really different about this scenario compared to the horizontal rolling the ball and the vertical throwing the ball straight up is that when you throw the ball at the angle like this, it does not travel in a straight line like it does in the other two scenarios. It travels in a curve. The other thing about this scenario is it's much harder to describe the direction of the ball. If the ball's just rolling on the floor, moving left-right, we can easily describe its direction using plus or minus. Plus for right, left, minus for left. If the ball is going straight up and then coming straight down, again, we can easily describe the direction using plus or minus. Plus for up, minus for down. But if the ball is kind of thrown at an angle, there's a lot more directions it can go in than just two. So we can't simply describe its direction by using a positive or a negative. We need to be a little more sophisticated. So we're going to have to start working with vectors that are being represented by arrows that can have many, many different directions. So before we get to solving those sort of problems, like the ball going on an angle, we have to get a bit more sophisticated and skilled in how we deal with vectors. And that's what this lesson is all about. So for starters, I want to review some things we've already discussed about vectors. And that is these 3 points. When I'm adding vectors together, so these are the rules we went over for adding vectors. When I'm adding them, I can put them in any order. Just like adding numbers, order doesn't matter. Each time I add a new vector to one I've already drawn, I start where the last one left me. Some people like to say we add the vectors head to tail, like elephants walking in the jungle. And after I've added my vectors together, the answer I get, which we call the resultant, goes from start to finish, from the very beginning of my very first vector to the very end of my very last vector. Okay, so that's how to add vectors. Now, let's pretend we wanted to do something a bit different. Let's pretend we wanted to subtract vectors. And I'll get you to imagine for a second that you have a friend who's great at adding numbers. They can add any two numbers you give them. You can give them integers, you can give them decimals, you can give them fractions, you can give them negative numbers, you can give them irrational numbers, any two numbers you think of. Give them to this friend, they can add them. But let's say this friend has never learned how to subtract. So if you give them a simple math problem like this, 4 minus 3, they freeze and they have no idea what to do. They've never seen subtraction before. How would you tell your friend to rephrase this problem in a way that they can understand? Remember, they can add any numbers you think of. So if you could rephrase this as an addition problem, they'd be able to do it. And what you're probably starting to think now is that 4 minus 3 can be written as 4 plus negative 3. One way we could say this is that to subtract a number, we add the opposite of that number. Opposite of 3 being -3. Well, this exact same idea, it turns out, works for vectors too. To subtract vectors, we add the opposite. So for example, if I have 4 up minus 3 left, that can be rewritten as to subtract a vector, I add the opposite. So the opposite of 3 left would be 3 right. And I can rewrite this as 4 up plus 3 right. And the last thing we might do with vectors is we might take a vector and multiply it by a scalar. And this one, you might be able to intuitively sort of figure out how to do it. Let's say I told you to take the vector 7 left and multiply it by 3. So what do you think 7 left times 3 is? Well, a lot of people would guess it is 21 left. And indeed it is. So what I've done here, this vector has 2 parts, the magnitude and the direction, as with every vector. And to multiply it by 3, I multiplied the magnitude by 3 to get the new magnitude, and the direction I left the same. And that indeed is how we multiply a vector by a scalar. We multiply its magnitude and keep its direction the same. Okay, so let's kind of do a couple examples of some simple vector math and draw out our result, our resultants. So 3 meters down minus 4 meters left. Here I have some subtraction. Recall from above that to subtract a vector, I add the opposite. So I can change this question to 3 meters down plus, and then the opposite of 4 meters left is going to be 4 meters right. Instead of subtracting this vector, I added the opposite of it. So let's try and draw that out. 3 meters down plus 4 meters right. Remember, I can add vectors in any order I want to. So rather than doing them in the order here, I might just reverse the order for fun. Both ways would be totally fine. So I'm going to do the 4 meters right first, and then I'm going to add the 3 meters down. So there's a vector showing 4 meters right, and I'm going to add to that one. So remember, when I add, the vectors being added have to go head to tail. So head to tail, here's my 3 meters down. Okay, this is 4 meters. This is 3 meters. And then my resultant goes from start to finish. Okay. Let's do one more example. 2 meters per second left plus 1 meter per second up times 3. Both of these questions have units in them. Don't really worry about the units. The idea is I can add, there are many different things that are vectors. You know, displacement is a vector, and these numbers over here likely represented a displacement. Velocity is a vector, and these numbers look like they represent a velocity. Acceleration is a vector as well, and force is a vector. And all these things have different units. So the vectors I'm adding could have all sorts of different kinds of units. But the units don't really matter for adding the vectors together. Regardless of whether the units are meters or meters per second or meters per second squared or newtons, I just do the same thing. I'm drawing the arrows out. So we have a little BEDMAS to deal with here. I have to add something and I have to multiply something. The order I'm going to do those in is the multiplication first. So rewriting this, it's going to be 2 meters per second left. And then 1 meter per second up times 3 is going to be 3 meters per second up. Remember our rule for multiplying a vector by a scalar is we multiply its magnitude and keep its direction the same, which is exactly what we did going from here to here. Okay, so we're now at a point where I just have two vectors that are being added together. I know how to draw that out, so let's do it. This time I'll just do it in the order they're given. So 2 meters per second left. And then plus, so I'm putting these guys head to tail, 3 meters per second up. There we go. And my resultant goes from start to finish. Okay. Now these resultants we've drawn give us sort of a rough idea of what the answer to this question would be. But they're not very precise. Because I'm just kind of sketching this, I'm not being particularly accurate. I don't know the exact length of this arrow I've drawn here, or the exact angle that it's pointing at. And we like to get to a position where, to get to a point where we can find those and communicate them. So if I wanted to write those resultants in words rather than just sketching them, that would give me an ability to be a bit more precise when telling someone what they are. So here's a couple of resultants or a couple of vectors that are drawn down. And I want to just show you the language we would use to sort of write these out in words rather than with these diagrams that are given here. So when I'm writing a vector out in words, I start by writing the magnitude. So the magnitude of this guy is like the length of this arrow, which is 12 meters per second squared. That's the magnitude of that vector. And then the direction I put after the magnitude, and I put it in square brackets. So the direction this guy is pointing, well, that's going to have something to do with this 15 degrees over here. But specifically, this 15 degrees compares my vector to what? It compares my vector to this line right here. And that line is a horizontal line. So the way I can be a bit more specific about the direction of my vector is by saying it is 15 degrees below horizontal. Right? Here's horizontal, and here's my vector 15 degrees below that line, below the horizontal. So that is sort of the notation and the language we use to communicate a vector's magnitude and direction when we want to write it out in words rather than drawing it. This part here is the magnitude. And this part here in the square brackets is the direction. Okay, let's have a look at this one over here. The magnitude is pretty straightforward to say. This guy's magnitude is 3 meters. And its direction is given with this angle up here, 50 degrees. And that angle is comparing my vector to this line. That line, unlike our last one, is not horizontal. This line is vertical. So here I had a horizontal line, and my vector was 15 degrees below it, so I said it was below horizontal. Over here, I have a vertical line, and my vector is kind of to the left of it. So I would maybe say it's 50 degrees left of vertical. Now there's another way we could say this, and this other way might be actually a little bit more common. It's sort of common practice, not really to compare vectors to vertical lines, like it's been done in this diagram, but to compare them to horizontal lines. That's the way things are normally done. And I suspect it maybe comes from a time when a lot of angles were being measured by sailors on ships to help with navigating and with the stars. And they always compared things to the horizontal because they always had a really good idea of what horizontal was, because they were surrounded by the ocean. And the horizon on the ocean gave a really good horizontal line they could compare things to. So it's common to compare vectors to the horizontal, not to the vertical. And we can do that for this vector here. There's a horizontal line. And I can find what the angle would be between the vector and the horizontal line. Because I've got a 90-degree angle here between the horizontal and the vertical, I know that this full angle from here to here has to be 90 degrees. Since this part is 50, the remaining part here has to be, what adds to 50 to give me 90 degrees? 40 degrees. So another way I could write this vector is 3 meters, 40 degrees above horizontal. Two ways to write it. Both are acceptable. Okay. So let's try and put this all together. Here we did some stuff where we did a little bit of math with some vectors. We found different ways we could write vector math. And we reminded ourselves that adding vectors was putting them head to tail, and the resultant went start to finish. And here we said, okay, if we have a resultant and we want to describe its direction in words rather than just sort of sketching it, this is some language we can use to do that. So now let's put it all together and let's take a vector math problem, solve it, draw it out, and find the resultant so precisely that we can express it in words using degrees for our direction. So, 5 meters left minus 2 meters up times 2. So in this problem, we got to do some BEDMAS here, some order of operations. I've got some subtraction I have to do and some multiplication I have to do. Order of operations tell me I should do that multiplication first. So 2 meters up times 2 will be 4 meters up. And now I'm in a position of having to subtract 4 meters up. To do that, I add the opposite. So the opposite of 4 meters up being 4 meters down. Okay, so to solve this problem, I have to do 5 meters left plus 4 meters down. I have to take those two vectors and add them together. I have to put them head to tail. So let's start doing that. There's 5 meters left. And here's 4 meters down. And my resultant will go there from start to finish. So I've kind of sketched it out, and now I want to find my resultant precisely enough that I can sort of write it down in words. So I need to know its magnitude, and I need to know its direction, just like we were doing up here, magnitude and direction. So magnitude basically comes down to finding the length of that line, which means I'm solving a little trigonometry problem here. This, if you haven't noticed, is a right angle triangle. So to find the magnitude, I am probably going to use Pythagoras, right? I have two sides of my right angled triangle, and I'm trying to find the length of the third side. Pythagoras will help us with that. So to find the magnitude, I'm going to use the Pythagorean theorem. A squared plus b squared equals c squared. Reminder, in a right angled triangle, C has to be the hypotenuse. It has to be the side that is opposite the right angle. A and B can be either of the other two sides. It doesn't matter which is A and which is B. So C is this side over here, and I'll make this side A and this side B. Excellent. So to solve for C, I'm going to rearrange this. I get C is the square root of 4 squared plus 5 squared. And that gives me C is equal to 6.40 if I go to 3 sig figs. Okay, so that's the length of this side here. That's the length of my resultant. I have found its magnitude. That should be in meters because everything in my problem was in meters. The next thing I need to do is find its direction. So one thing to note is we always define a vector's direction from its tail. So to give the direction, like we did up here, every time I set a direction, it involved an angle, a number of degrees. So I'm going to need to find an angle. And the angle I'm going to use is not an angle at the head of this vector, but an angle at its tail. So we're going to find the angle in the triangle that's at the tail of the vector. That guy there. And that's my unknown. That's the thing I'm looking for. When we're doing algebra and we have like a number we're trying to find, we often call it x. When we're doing trigonometry and we have an angle we're trying to find, we call it theta. Sort of like a O with a belt. So reminder here, when we define a vector's direction, we always do it from the vector's tail. So how am I going to find that theta? Well, I'll remind you, when we're dealing with a right-angled triangle, we have three trigonometry ratios called sine, cosine, and tangent. And the little mnemonic that most people use to remember how to use them is this. So, ka, toa, which is a way to remember that sine of theta equals the opposite side divided by the hypotenuse. Cosine of theta equals the adjacent side divided by the hypotenuse. And tan of theta equals opposite side over adjacent side, right? Sine is opposite over hypotenuse. S is O over H. So let's have a look over here at our angle we're trying to find. I'm trying to find that angle. So first of all, it might be worth figuring out which side is the opposite, which side is the hypotenuse, and which side is the adjacent. So the hypotenuse side we already identified as C. That's my hypotenuse. It's the side that's opposite the right angle. The opposite side is usually the next easiest one. Here's my angle. So I go far away from it as I can on the triangle and I get over here. That side is the side that's opposite the angle. And then the adjacent side is the one left over. It's the side that is adjacent to or beside the angle and isn't the hypotenuse. So there we have my opposite, my hypotenuse, and my adjacent. So to solve for theta, I have to pick if I'm going to use sine, cosine, or tangent. In this question, at this point, because we actually know this side, and this side, and this side, because we found C, I could use sine, cosine, or tangent. All three of them would work. But what I'm going to do is, because A and B were sort of given to me to start with, and C is one I calculated myself, I think I trust A and B more. There's a chance I made a mistake when I found C. So I'm going to pick a trig ratio that uses A and B, that uses the opposite side and the adjacent side. That way, if I made a mistake over here, it's not going to carry over into my direction calculation as well. So what trig ratio uses opposite and adjacent? That's going to be tan. So let's calculate that. We know that tan is opposite over adjacent. Sorry, I should write that as tan of theta is opposite over adjacent. And in this case, I actually know the opposite and the adjacent, so I might just plug those numbers in right off the bat. The opposite side is 4, and the adjacent side is 5. Right, so that tells me what tan theta is, but what I want to know is just theta by itself. So I have to do a little bit of algebra here. Now, if theta was being multiplied by something, and I wanted to isolate it, I would divide by that thing. If theta was being added to something, and I wanted to isolate it, I would subtract. But what's being done to theta here is it's being tanned. It has this tan function that's being applied to it. So how do I undo a tan function? Well, that is done with the inverse tan function. So to get rid of my tan and get theta by itself, I'm going to put an inverse tan, or tan to the minus 1, in front of it. Let's just move this down a little bit. And the rule is if I do something to one side, I have to do the same thing to the other side. That's sort of basic algebra. And then the idea here is these two tans cancel out. Inverse tan and regular tan cancel each other out. So I'm left with, on the left side, just theta, which is what I wanted, is inverse tan 4 over 5. And that gives me theta equals 38.7 degrees. So, when asked to take this vector problem and solve it, I did some order of operations and I changed it so it was simple vector addition, one vector plus another. Then I drew them out in this triangle here, and I drew out what the resultant would look like. Then, to actually find that resultant in numbers, I used Pythagoras to find its magnitude, and I used SOHCAHTOA to find its direction. That gave me this number here and this number here. So now I'm ready to write my final answer, to write the magnitude and direction of that resultant. So its magnitude is 6.40. And that number is going to be in meters, right? We were working with meters in this problem. And its direction is 38.7 degrees. That's this guy up here. And that shows my vector as being below this horizontal line. That angle compares the horizontal line to my vector there. And it shows my vector being below the horizontal line by exactly that many degrees. So my vector is 38.7 degrees below horizontal. And that is our final answer. So, quick recap. Vectors have magnitude and direction. If I want to multiply a vector by a scalar, I multiply its magnitude and I keep its direction the same. If I want to subtract two vectors, I simply add the opposite. And once I do all that, I can reduce my problem to simply adding vectors, in which case I have to remember that order doesn't matter. The vectors being added have to be head to tail, and the resultant goes from start to finish. Then we did some practice of that here. When I'm writing out the direction of a vector, I use square brackets like this, and I use a number of degrees to compare my vector to either a horizontal line or to a vertical line, preferentially to a horizontal line. When I actually have a vector and I'm trying to find its magnitude and direction, I'm trying to be specific about it, I use a little bit of trigonometry. I can use Pythagorean theorem to find the magnitude of the vector, and I can use SOHCAHTOA, my basic trig ratios, to find the direction. When I'm trying to find the direction, I have a few options. It would appear as to what angle to pick, because every triangle has a few different angles in it. So just remember that the one we want is the angle at the tail of the vector. We always define a vector's direction from its tail. So, not a lot of physics in here, really. Mostly just sort of some math review and learning some new sort of syntax and phrases that we'll use for kind of communicating this information in physics class. But this lesson, if you understood it, puts you on sort of a good footing to start looking at problems where we have vectors or where we have motion in two dimensions. Not just left, right, not just up, down, but both at the same